Introductory Neuroscience and Neuroinstrumentation, Introduction to Event-Related Potentials. So hello, in this session we shall introduce ERPs, Event-Related Potentials, a very important tool in cognitive neurophysiology. So the next two lectures are the heart of the course. So far we've got the background on the brain, a little bit of its anatomy, a little bit of its physiology, a little bit of how cells, nerve cells can be stimulated, etc. So now we will get into event-related potentials, where we record activity from the scalp. It's non-invasive and it's tolerated very well by most people. So EEG, electroencephalography, is the continuous electrical activity recorded from the scalp. An event-related potential, on the other hand, is the average electrical activity which is time-locked to a specific stimulus. It could be a tone, it could be a click, or it could be a flash. So it could be, ERPs can be auditory, visual, or somatosensory, that is touch. Evoked potentials are used in neurology, and they are a subset of ERPs, and they are the auditory evoked potential, the visual evoked potential, and the somatosensory evoked potential. So they are easy to record, they are non-invasive, and they are relatively inexpensive compared to fMRI. It's another technique to look at brain function. Okay. So they have the highest temporal resolution, measured in milliseconds. So EEG, ERP, MEG are right up there, and they have millisecond resolutions. Further down, you have MRI, PET, fMRI, and these look at brain activity in multiple seconds or tens of seconds. Okay, and finally, you have single cell recording and microstimulation. We're not talking about that over here. So as far as the whole brain recordings are concerned, EEG, ERPs are the best. MEG is the recording the magnetic fields of the brain. If you remember your Fleming's laws, the electrical field is perpendicular to or orthogonal to the magnetic field, except that is you need a special recording setup using squids, not the squid we were talking about, but superconducting quantum interference devices, and that makes it very expensive to deploy on a large scale. So EEG, ERPs still remain the simplest and the most cost-effective tool to look at brain function. So let's start with the electrodes. What are the best electrodes to use? You want electrodes which don't, take part in the phenomenon, contribute to the electrical activity, and thus far we have found that silver electrodes are the best. Now silver forms a layer of silver chloride between the silver and the scalp, and this, with this, biopotentials are not distorted, they are easily recorded. And between the electrode and the scalp, we over here we use conductive gel. This is basically something which conducts, has got salt in it, and it provides a good interface between the electrode and the biological tissue, in this case the scalp. On the side you see gold-plated electrodes, which are alternative. They are inert and they are typically used in clinical practice. So what we do is, first we clean the scalp and abrade it slightly so that the impedance at the scalp is less than 2000 ohms. It's important to use antiseptic precautions, because you can cause infection if the electrodes are contaminated by previous recordings. And typically the infection one is worried about in clinical practice is hepatitis B infection. And the input impedance of the amplifiers tells us what would be the optimal impedance we need over here. So typically this impedance has to be much less compared to the input impedance of the amplifiers. So if it's 2K, the input impedance of the amplifiers would be probably like 10 megs. Okay. And where do we place the electrode? So this was a system for EEG electrode placement, which was first propagated and popularized by Jasper, a Canadian EEG researcher. So here you have This is from the top, and this is looking at the left side of the brain. So from the top, your central electrode, or central electrodes, the ones over here, are all denoted C with a subscript depending on whether you're on the left side, in which case is an odd number, and if it's on the right side, it's an even number. So in front of CZ, anterior to it, are the frontal electrodes, and FP1, FP2 are electrodes on the forehead. Behind you have the parietal electrodes, and right behind you have the occipital electrodes. So the convention is that on the left side we have odd numbers, on the right side we have even numbers, and the central electrodes have a subscript of Z or Z. So you have PZ or PZ, which is central line parietal electrode. OZ is not shown over here, it's below, so it's the occipital electrode, center electrode. CZ is probably the most important electrode in the central electrode. Frontal FZ is the midline frontal electrode, and so on and so forth. Okay. So traditionally you have to clean each area and then affix the electrode on it so that the impedance goes down. But now we have advances. First of all, we have caps where the electrode positions are already pre-marked. Just put on the cap and you don't have to measure it, because with the FZ, with the electrode placement convention, you have to measure the distance between the nasion and the inion, between the two preauricular ridges over here, join these two lines, and then you get CZ. And now you take 10% and 20% of this length, and there with that you get the other electrode positions. So it's a painstaking method, especially when you have 40 electrodes or more. We have to mark each electrode and make sure that you're in the correct position. Current day technology have a cap where these electrode positions are pre-marked, so you just put on the cap. And also they use dry electrodes. With dry electrodes, the impedance is very high of the electrodes, anywhere from 50 to 150 K. But correspondingly, the input impedance of the amplifiers are much higher, 10 to the 12, for example. Okay, so you get recordings. They'll be slightly noisy, but very good recordings within seconds. This Inobio is made by Neuroelectrics. It's an FDA approved and CE certified system, which we use in our lab both at St. John's and at IAC. It is a little expensive, but if you want to do it yourself and get good recordings, but on a bare bone system, I strongly recommend OpenBCI. This is not certified for regular clinical use, but it's okay for doing research. And these are also, even though it uses wet electrodes, dry electrodes also work pretty well. This is an Electrode EEG cap for a child. We make it friendly by putting a Mickey Mouse overlay on it. And finally, I have to mention gamer systems used by gamers like Emotive and NeuroSky, where you can record EEG and ERPs. However, these tend to be noisy, and usually neuroscientists hesitate to use them in an official study because they are not certified for clinical or research purposes. But again, in a pinch you could use these, and many people have. Many students and researchers have used these systems. So what are the stimuli? So we went through the electrodes, we went through the impedances, we went through the positions. Now coming to the stimuli. So auditory stimuli, we typically use clicks, which is a square wave, 1 millisecond or 0.1 millisecond, or we use tones, discrete tones of particular frequencies, 500, 1000 hertz, and this is a tone. It's a pure tone. Above it's 1000 and below it's 1100. It's too close for us to make out a difference, and these were generated using the open source program Audacity. Okay. Alternatively, these are pure tones. Alternatively, we can have a white noise burst like shh, or we can have a vocalization like da. So this is a white noise burst, and this is da, which is a stimulus developed by Professor Nina Krause's lab at Northwestern University. Both of them are approximately 40 milliseconds. Okay. Notice the complex structure of 40 milliseconds of da. Okay. You can also use visual stimuli. I happen to use alphabets over here, Hindi and Kannada, but you can use English alphabets, pictures, faces, what have you. Okay. So this is from our lab, where this is the electrode montage. So here we have midline electrodes, and we have some temporal electrodes and electrodes on the headband on the side. This is the free running EEG. Once we record the raw EEG, we do the processing. This is a choice. We do the processing in ERP lab or EEG lab, which are open source modules which work on MATLAB, and they have been there for more than a decade, and they are designed to analyze ERPs and evoked potentials. And after we have to do processing. Typically what we do is we have a stimulus, so we take an epoch time lock to the stimulus a little before the stimulus begins for getting the baseline, and then for about 1 second to get the phenomena of interest. Then we reject all the artifacts, which are eye blinks, movements. All these are muscular artifacts which will swamp the EEG. So we keep a window and windowing threshold plus minus 100 microvolts, for example. Anything above or below, we throw it out. And then we filter it. The EEG frequencies of interest which we record from the scalp are all below 100 hertz. Okay, so we can use a filter, usually a bandpass filter, 1 to 30 hertz, and that gets us all the information we need for ERPs. So typically what information we need amplitudes, we need latencies, and so on and so forth. Okay. After we have done all this, we average it. Why do we average it? We average it so that when we are doing the ERP experiment, the person is thinking, a lot of different things are happening in the brain besides listening or paying attention to the tone or the visual stimulus. So when you average, only the common features of the stimulus invoked response remain. All the other stuff is thrown out. So that's the importance of averaging. Okay. So the free running EEG, we have stimuli coming in at regular intervals, it's time locked, so we create epochs, we reject the artifacts, we filter, and then finally we average. So that in brief is how we analyze the raw data to get ERPs. One point, as a person in bioinstrumentation or in medicine, you will often encounter clinical grade EEG systems. Some models are Nicolay and Nihon Kohden. They're very, very good for clinical work. Okay, they're not very useful for research because you have to be able to have complete control over the stimulus modality, modify it, get external triggers, so on and so forth. And these do not do that. They are meant for technicians who just sit over there. You have pre-made evoked potential stimuli, actually, mostly auditory evoked potential, visual evoked potential, and somatosensory evoked potential. And that person sits over there, punches a few buttons after placing the electrodes and gets the data. But they're very good clinical systems. They can take a lot of abuse in the clinical wards, and in hospitals, if they have ERP, EEG setups, it's one of these or something similar. If you're really, if you have the talent and you're really macho, and if you want to do it yourself, it's possible. You can build bioamplifiers which do all this stuff. So this is from a Japanese group, Matsuzaka et al. And all amplifiers, biological amplifiers, have this similar kind of meta schematic. You have your electrodes over here, and they have to be shielded because otherwise they'll pick up AC. Then you have an input stage amplifier, which kind of basically impedance matches between the electrodes and the rest of the signal conditioning circuit. There is no real amplification over here. The next stage, you have a broadband amplifier of the particular, and usually, it's of a particular level, 1,000, 2,000, 10,000, like that. If it's too much, you can cut the gain. So you have a gain control stage where you can modify the gain. And finally, you have bandpass amplifiers where you filter and look at only the frequencies of interest. Okay. So this is a general, logical signal conditioning circuit for EEG. So it is also possible, now all these systems are very expensive. Typically they cost $50,000 to $100,000. So you can also build it yourself. So you're using a judicious combination of Arduino and Raspberry Pi. So our group presented a circuit where we used Arduinos to generate the trigger, And then we use another Arduino to generate clicks or tones, and that goes through an audio amplifier, and the outputs are a stereo headphone or a speaker heard by the subject. That is for auditory stimuli. For visual stimuli, we use a single board computer, typically a Raspberry Pi, and you can run PsychoPi, which is a program from Professor Jonathan Pierce, and that generates auditory and visual stimuli. The electrodes are, you could use the previous circuit, this circuit, Matsuzaka circuit, and we made this circuit in our lab. So these get the inputs from the electrodes, and you combine these, you integrate the triggers from the stimulus trigger generator with the responses, and you do the analysis either on an oscilloscope, which is the traditional way to do it, or you can take it through a DAC, an A to D conversion, and take it into your laptop and do the analysis. So what are we recording when we put in electrodes on the head? So there is something called the inverse problem. There's a whole lecture on it which will be done in a subsequent week. But briefly, you have all the pyramidal cells. If you remember the pyramidal cells, the cortical columns and stuff. So you have an axon coming from a lower area, the thalamus. It goes just above the soma and it depolarizes it. So as soon as it depolarizes here, this area gets hyperpolarized. So there's a dipole which is formed, and if you have the electrode on top, you have a positive reflection. Now this is an interesting tradition in neurophysiology. Negative is often shown as up and positive is down. Okay, keep that in mind. So this is a positive deflection. Alternatively, you can have inputs to the pyramids from the opposite side, the contralateral cortex, and then the opposite phenomena happens. It depolarizes this area, the dendritic branches, and there's hyperpolarization over here. So here you get the opposite deflection, and there are many combinations. Okay, but roughly this is what is recorded, and we do not record action potentials. We record postsynaptic potentials, typically excitatory postsynaptic potentials. Action potentials occur, but the scalp acts as a low pass filter. It just filters out all the high frequency action potentials, and you only get the low frequencies. So current understanding is that the EEG, ERPs, all the stuff we record on the scalp is due to postsynaptic potentials. So free running EEG, brain waves. So this is a traditional way of recording EEG. You put two electrodes on the scalp, amplifier, and in the old days they used a stylus and a running paper sheet, which the stylus would track the EEG on it. So you have different frequencies, and they're all low frequencies. Okay, so deep sleep, you have frequencies less than 3-4 hertz. When you're drowsy and kind of getting there, a little sleepy, you get the theta band, which is 4 to 8 hertz. So the first one is the delta band, less than 4. Then is the theta band, which is less than 8, 4 to 8. Then you're awake, but you're resting, and sometimes your eyes are closed. You get this typical alpha activity, 8 to 13 hertz, and that's recorded best on the occiput, on the back of the head. Right on top is beta activity, which is the normal mental activity, 15 to 30, 14 to 30 hertz. And the beta activity is high frequency by EEG standards, but low amplitude. While all the rest, the lower the frequency gets, the amplitude increases. So Hans Berger showed alpha waves, and he was a psychiatrist from Jena, University of Jena in Austria, and he won the Nobel Prize. He was the first guy to show electrical activity could be recorded from the scalp. Of course, no one believed him, so it took many years for people to come around and independently replicate it, and before they believed him. Okay. So let's start with the auditory system. So this gives us, we hear clicks, and as soon as we hear clicks, we record from the scalp, and this tests the pathways, the auditory pathways, right from the periphery, the tympanic membrane, the eardrum, through the cochlea to the brainstem, multiple pathways, and primary auditory cortex. The whole auditory pathway is checked by the auditory evoked potential. So the stimuli are typically clicks for auditory brainstem responses at 90 dB and 100 hertz, or for the auditory evoked potential you have tones, tones of 100 millisecond duration, usually about 65-70 dB. And these tones should have on ramps and off ramps, otherwise if they are abrupt, when you do FFTs you might get edge effects. Okay. Right. So on the in the middle you see a typical circuit where you have recording electrodes, one on the top, one on this here, and there's a ground, and you hear the sound, and the sound is given by an HP click or tone generator, and you get recordings like these. Please note that this is a logarithmic x-axis, so 1 to 10 milliseconds is where you get the auditory brainstem responses. You have a set of wave stations, if you will, 1 to 6, 7 waves. Then you have the middle latency responses, and then you have the auditory evoked responses, what we usually record, and our most important potentials are or components are P1, N1, P2, N2, P3. So P1, P2, etc. stands for the first positive component. N1 is the first negative component. Okay, that's the nomenclature used in ERP component analysis. Similarly, with the visual system, you check the visual system from the eye through the various pathways, and you record from the occiput at the back. And you can either use a flash, or what they do in clinical neurophysiology in the hospital is you have a checkerboard, a chessboard, which keeps reversing. The squares alternatively are white or black. And again, you get an N1 response, a P1 response, and an N2 response. So first negative component, second negative component, first positive component. Now these components, they're similar to the auditory components, but they're just components. They have very different underlying mechanisms and neural tissue involved. Okay? And this potential is delayed if there is a problem with the visual system. Like for example, multiple sclerosis. We learned about myelin. So sometimes the body destroys its own myelin through an autoimmune process. That's a disorder. And the conduction failure occurs. First latencies become longer, and then finally you have conduction failure. The nerves don't conduct. But in the process, in the intermediate process, when the latencies are getting prolonged, you can easily see that here. In fact, for multiple sclerosis, visual evoked potentials are the diagnostic criteria. The other diagnostic criteria is you actually show the antibodies. But it's pretty obvious, and it's very common that you have delayed components, visual components in multiple sclerosis. And this is because multiple sclerosis can affect the brain randomly. However, 40% of the brain arguably deals with the visual system. So one of the first signs that of multiple sclerosis is prolonged latencies in the visual evoked potential. Okay. So we finish auditory, we finish visual. Now we come to the somatosensory. Here we give a brief electrical pulse either to the ankle, or we can give it to the median nerve at the wrist. And we monitor the potentials as it goes up to the brain. Okay. So right over here at the knee, it's very early. Then at the spine, at the lumbothoracic spine, it's a little later, and it gets more delayed as it goes up. And finally in the scalp, the brain, you have the somatosensory evoked potential. So for the somatosensory evoked potential, this would be P1. The 37 indicates the latency in seconds from the stimulus, from the time it takes to travel from here to here. And similarly 45, it's the N1, but it takes 45 seconds to go from milliseconds to go from here to here to record this component. Okay, and this is used typically intraoperative monitoring during spinal surgery. So the neurosurgeon is operating somewhere here, is trying to typically you're trying to straighten the spinal cord because people have scoliosis, their spines are bent, or it's bent in front, kyphosis. So you put rods in the spinal cord and pull the bone back and straighten it. In this process, the spinal cord can get damaged. So if we are monitoring this continuously before, during, and after surgery, we can tell the neurosurgeon, hey, stop, because you're doing something which is causing these potentials to go down. And typically, the neurosurgeons are very good. It occurs very rarely. And typically, if they reverse what they're doing within seconds, it comes back to normal. If it's not reversed, and then it can become a permanent problem. The problem with doing neurosurgery is that unlike blood vessels, if you chop a blood vessel, blood spurts and you know you've done something wrong. But in spinal surgery, if you chop the spinal cord, there is no indication that anything has happened. It's all just grayish, whitish matter. So this is a very important way to monitor, the spinal cord during surgery and make sure that you're not causing problems due to the surgery itself. Okay? So thank you, and in the next session we will get into more details of event-related potentials.